doubts you have, then sir will give it to you. So I hope this is clear. I hope you understand. So thank you so much, and let's start the session. So okay, so let me start from the beginning. So what actually is Simon algorithm? We will start with Simon algorithm. Today our agenda is to yes. Is my screen visible and I'm audible, right?
Yeah, you are visible and audible.
Yeah. Okay. So can I start, sir?
You can start.
Okay. So today we'll be discussing about Simon's algorithm, and we will also brief about some part of. I have a brief about some hybrid quantum algorithms also. I will not go in depth because we have some time constraints. I will just explain what are the existing hybrid quantum algorithms present, and then I will just say the application areas. And yeah, so let's get started with the Simon's algorithm. So Simon's algorithm is actually an essential quantum algorithm, which is introduced by Daniel Simon. We all know that the name is derived from the person who was discovered this, was introduced this algorithm, quantum algorithm. So this happened in 1994, like around 30 years ago. So Simon's algorithm is the first algorithm to actually showcase some exponential speed up in quantum. Till that time, only the classical algorithms were there, but he is the first person to actually showcase the exponential speed up in quantum. So the main motivation behind Simon's algorithm is actually to provide a clean and provable example where quantum algorithm actually beats a classical algorithm exponentially. So what is that classical algorithm he wants to beat up? So he got an inspiration from the best classical algorithm called brute force squaring algorithm. So that's the algorithm which is giving some nice results in the classical domain, but but the time complexity was exponential in nature. But Simon wants to prove in polynomial time. So Simon wants to prove that quantum can perform better than the brute force squaring algorithm, and that's why he started this quantum algorithm chapter itself. He started because of him, to prove that quantum is no lesser than classical. Okay, so in classical method, so what do we use in the classical method? So we know that the best classical algorithm is brute force squaring algorithm, right? So in classical method, so the main concept is to find a hidden string called S. Okay, in classical method, in especially the brute force squaring algorithm, to find a hidden string S, there is no particular structure to exploit. Okay, so for example, as I mentioned in last session, in yesterday's session, that if you put a 2 rupee, 1 rupee coin among inside so many millions of 2 rupee coin, and finding it in a very shorter time is very difficult, right? So there is no structure for this classical method. It has to do some trial and error method to actually find out the possible 1 rupee coin. Okay, so so when you do trial and error method, it takes a lot of time. You can imagine just like you are a small child and your parents are saying that don't touch the flame, you will get you will get burnt. But as a child, we will not listen to the parents, and we will do trial and error method, and we try to touch the flame, and what will happen? We will get burnt. So it's something like that. Okay, so it does it. So it's like how we do trial and error method, and we find the best possible solution for any kind of problems. Just like we have some issues and we try to think into different consequences, and we find some possible solution, right? In the same way, the classical method also is there. For example, you can also assume that you have a mentor in quantum computing, and he or she is teaching everything to you. So your time of trial and error method is kind of saving, right? So that's what Simon's algorithm is. So when you study quantum on your own, you are like in a classical algorithm side. Okay, you have to do a lot of trial and error method. You have to understand a lot of math. You have to understand yourself, physics, and everything. But you have a mentor who is well experienced. You can learn it from them, and of course you have to do self study. But if you have a mentor, you can understand their teaching, right? Then half of the understanding is done by just listening to them. So that's how the classical method and Simon's algorithm, what I'm trying to explain. I'm just trying to give you an analogy so that you can understand much better. Okay. So I hope this analogy is a bit more clear. Okay, let's continue. So in Simon's, so as we mentioned in classical algorithm, there is no proper structure to exploit because it has to run in the trial and error method to find the best possible solution. So that it takes time. So exponential method takes a lot of time. It may also degrade when it takes more time. It can it may not find the solution also. So that's the problem with the classical method. But in Simon's algorithm, the input itself is put into the superposition state. So in real life, which we are going to solve. So how do you put in the superposition state? By using the edge gate. Okay. So when you put the input state itself in the superposition, and you give it to the oracle, and the oracle will find best solution for you. So in that case, the quantum is actually much better, just like how you have a mentor in quantum, and he has done all the hard work for you, and he's just teaching you have to listen, and you're giving an exam and you're getting good marks, just like that. Okay, I hope this analogy is clear. Okay, yeah, I've given just a small table approach, like what is the classical one and what are the complexity and what is the method. So in classical approach, you use, 2 to the power n by 2 queries, which is the method which is used is brute force method, and it is an exponential, it goes exponentially. The time taken to solve is exponential in nature. So what is the meaning of exponential? Exponential means it takes a lot of time to even find the best result. So if it takes a lot of time, it can get the result. After spending a lot of time, it may not get result also. So, okay, so that's the main issue with the classical. But in quantum, especially in this particular algorithm, it uses O to the power n, O n queries, n queries, which means it uses a polynomial time. So polynomial time is kind of quicker to find a solution. Okay, so what makes it more quicker to find a solution? It uses superposition and interference. So superposition interference we might have already seen in the previous sessions. Okay, so in this Simon's algorithm, we are putting all the input into the superposition state to find the best possible solution, and giving it to an oracle, and the oracle finds a best possible solution for you. Okay, so that's what Simon's algorithm is. So actually, Simon's algorithm was created to answer a deep theoretical question in the early 1990s. So what is that question? Whether can a quantum computer be exponentially faster than a classical one? Like I mentioned in the previous slide, like whether a quantum computer can be exponentially faster than a classical one, even for a very simple black box problem. Okay, that's the reason Simon, there was a question in Simon's mind. So he was thinking whether quantum computer can perform better or not. Okay, just even for a simple problem. So at the time, even you know that there is a particular algorithm called Shor's algorithm, which is about the RSA encryption for the quantum cryptography side. It is said that it can break the classical encryption scheme, but I don't believe that, because you need millions of qubits to break the classical encryption scheme. Okay, if someone says that you can break the classical cryptography, please don't believe, because it takes a lot of qubits to even break it, because classical encryption scheme is not it's not just a joke, because it has evolved for decades and decades. Okay, so don't trust that people say that RSA encryption, Shor's algorithm can break classical. No, it doesn't happen just like that. Okay, so even before Shor's algorithm, Simon has actually uh, I mean experimented this clean proof of concept method to prove that quantum computer can be exponentially faster than the classical one. Yeah, as I mentioned in the previous slide, so our main target in the Simon's algorithm is to find the hidden string S, where when you give a function f with the property f of x equal to f x x or s. So s is actually the bit string, hidden bit string. Okay. Then quantum algorithm uses only n queries, like as I mentioned, by using superposition plus interference. So the main intuition behind this motivation is classical algorithms can only discover S by trial and error method, two inputs that give same output. So this two inputs that give same output is you don't have to worry. Yesterday I said that if you give two input and you get the same output, it can be many to one mapping. But here we use these two inputs and same output during the measurement. So when you measure something, that mapping, that part doesn't come under the measurement. Measurement is just a method to find a solution to the problem. Okay, so we use this technique in the measurement side only. So you don't have to think that I have said this differently and today is something different. We are using the technique in a different way. Okay. Um, so quantum computers actually put all the possible state into superposition and ask the oracle about all of them simultaneously. And we have also discussed what is the meaning of oracle in the previous session 5 yesterday. So to give a very short introduction, oracle is nothing but a reversible version of the Boolean function, which has taken inspiration from the classical algorithm, and we are converting into the reversible version of the reversible version by adding an extra target bit plus an XOR gate. Okay, so that in that sense you get a reversible version of the Boolean function, and that's what an oracle is made of. Okay, so the motivation was to demonstrate that quantum mechanics allows a fundamentally different way of extracting quantum information from a function. So the main motivation for the Simon, the researcher Simon, is to actually demonstrate that quantum can be different, can fundamentally work different than a classical algorithm and find best possible solution. So that was his main motivation, to prove that quantum is better. Quantum is also best, same like how classical algorithm is also best. Okay, so now why Simon's algorithm is a breakthrough in late 20th century? The main reason is because it was the first problem showing its exponential separation between classical and quantum query, because this came in 1994, and Shor's algorithm was directly inspired from Shor's algorithm. Okay, because Shor realized that Simon's hidden XOR mask trick generalizes to hidden periods in the number theory. So in short, Simon algorithm was the prototype that actually proved quantum computing is more than just a hype. So if you want to give some appreciation to the present advancements at this time, you can give that appreciation to Simon, because he is the first person to even start that and prove that quantum is definitely better than classical. So we should all give a big round of applause to Simon. Okay, so it's not about solving a practical problem at first, but about proving that quantum algorithms can be exponentially faster than the classical ones by leveraging, again, superposition and interference. So that's the difference between classical and quantum. So classical doesn't use any superposition and interference. So only quantum has this capacity of using putting all the inputs in a superposition state and using the interference pattern to extract the global hidden structure. Okay, so this is the theoretical part, and next two slides are about the quantum. Hybrid classical quantum algorithms. Just two slides is there. So now I will be discussing about the mathematical derivation of the Simon's algorithm, and then after that we can see how about the hidden, hybrid quantum classical algorithms. Okay, so I will quickly unshare and share my screen again.
Ma'am?
Yes, sir.
Hello.
I'm just sharing my screen once more. Yeah. Yes, sir.
Okay, no issue.
Yes, sir. I just mentioned that I will be, unshared my screen to share that notepad, So,
No issue.
okay, sir. Is my, I think my
Yeah,
screen should be visible, right? Okay.
it is visible.
Okay, my screen is visible, right? The iPad.
Yes, ma'am, it is visible.
Okay, sir. Thank you, sir. Okay, so now let's start with the mathematical derivation of the Simon's algorithm. We are going to generalize the Simon's algorithm, means we are not going to decide how many qubits a Simon's algorithm should hold. So it can be any number of qubits. Okay, so we are just going to make sure that we are going to generalize the Simon's algorithm, and that's what all the quantum algorithms are. We only generalize uh, any algorithms, so that if you need two qubits, you can solve that mathematical derivation and get it. So even a mathematician actually generalizes the whole equation, not just particularly point out and write. Okay, so that should answer your question, why are we generalizing the any algorithms. Okay. Okay, so let's start. Simon's algorithm actually involves finding a secret n-bit string by querying an oracle. Okay, so that oracle takes a n-bit string. The oracle takes a n-bit string x equal to x1, x2, x3 till xn. Okay, as input, and it outputs and it an n-bit string f of x. Okay, so now let's just draw a simple circuit diagram. I mean, quantum circuit for the Simon's algorithm. And with this only, we are going to do mathematical derivations. Okay, so this is an H gate. So this actually H gate will put the inputs into the superposition, which we have discussed in the slides. Let me draw a bit more bigger. Okay. This is actually called as a tensor product. Okay, and this is actually n. N is nothing but n number of qubits. Okay, we don't. That's what I said. We are not going to specifically mention how many qubits we are working on. We are using n because we are generalizing it to n number of qubits. That n number of qubits can be 1 qubit also, 100 qubits also, 200 qubits also, 500 qubits also. So why we are using n qubits? If it is 1 qubit or 2 qubit, we can just write 1 and 2. But what is it? What if it is more than 5 qubits, 10 qubits? You can't keep expanding everything, right? So why we are generalizing it? I hope this should make more clear now. So we are actually drawing an oracle now. Yesterday's session, we just explained what is an oracle. Now we are actually solving using an oracle. This should make yesterday's session a bit more clear. Okay, this is an oracle, and this is a Hadamard gate. Okay, again we are giving Hadamard gate. Okay, why we are giving to Hadamard gate? Because we need to reverse. If we kind of do H dagger, H dagger, you get identity operator, right? So that's the reason, which means it is a unitary operation. And before this, we are measuring here. So this is actually called as a measurement. Measurement means we are actually coming to a conclusion. We are finding a solution. We are collapsing the state. So usually the input actually in this, we are giving edge gate, which means putting all the inputs in the superposition state. Okay, if all the inputs are in the superposition state, there is a lot of probability attached to every state. Okay, so when we collapse the state, the answer will be only particular states. Means whatever value, whatever amplitude attached to that particular state, you will get that. So why we are collapsing the so why we are measuring to find the solution. And then again, we need to measure the first register. Okay, so this I will write it as pi1. This is nothing but a state. Okay, every step I'm writing, these are actually the steps. We will see that when I solve it. Okay, I will explain that. So this is 5, this is 6. So this is first register. Tensor product n. This is initialized to get 0. Again, the n is called as number of qubits. This is a second register, and again this is n. Okay, so I want to mention that. So first register as n number of qubits means, so first, so it's like a box. It's you can consider this first register as a cartoon box where you have where you can put all the items, right? Glass items or any other items. So just like that, register is like a bundle of multiple many number of qubits. Okay, and second register is also n qubits. So this is an input register, and this is an output register or target register. Okay, I hope this is clear. Okay, so we have an oracle. Yesterday we have mentioned about the oracle. That we also saw mathematical expression for this oracle form after we adopt to the quantum version. So y is actually an extra bit, target bit we're adding, XOR f of x. Okay, so let's start with step 1. So step 1 is initialize. So this is get 0 into get 0 tensor product number of qubits. So this is nothing but I'm just in, this is the first stage. So I am doing this first stage. Okay, so let's start with the first stage. So I'm doing the first stage. Next is step 2. So first step is initializing. We are initializing the register, each register to get 0 tensor product n number of qubits. Means for in every register you have multiple qubits, and we don't know how many qubits are there. So why we are generalizing it. Okay, so put the input register in uniform superposition state. Okay, so we are applying. So if you go back, you can see that the Adamant gate is actually applied to the first register. What is Adamant gate? Adamant gate gives you superposition. So when I was explaining you with the help of slides, I mentioned that all the inputs are actually in superposition state, and that's what exactly we are doing here. So the superposition state is achieved by applying an edge gate. So edge gate gives you superposition. Okay, it's a linear combination of multiple states. That's what superposition means. Okay, so when you are apply to register 1. So before that, we will just see the representation of H gate. So where H gate, when it is applied to gate 0, you will be getting 1 divided by root 2. 1 divided by root is nothing but the probability. So gate 0 is in 1 divided by root 2 probability. When you take the square of this, root square of this, you will get 0 0.5. 0 0.5, and you 0 0.5 plus 0 0.5, you get 1. So that's how the state should be equal to 1. Okay, so for so this, you might already know this. Okay, I'm just giving a short introduction for this. So for n qubits, when applying edge gate, okay, so we are applying edge gate to n number of qubits. Okay, so h try to n qubits. I mean, H applied to the first register means it has a lot of multiple qubits. So 0, so 0 is initialized 1. So we get 1 divided by root 2, get 0 plus get 1. Okay. So if you take this inside, you get 1 divided by root 2 n, get 0 plus get 1 into, I mean, tensor product. It's not into, it's tensor product. So we have just discussed that register 1 as n number of qubits. So register 2 as also n number of qubits. So we are um, and we are applying H gate means we are applying the H gate to that much amount of qubits present in the register number 1. So we are labeling that in qubits as X. Okay, so yeah, why we are labeling that n? So I was discussing about n qubits. This much number of qubits are there in the first register, right? We can label them as X. Why should I label them as X number of qubits? Because if you see in this oracle, this X is the first one, and this is the second one, right? So what is first and second? This is the first register, means this is the first register here. Okay, this is the first register. This is the first register, and this Y is the second register. That's why we are labeling for our convenience purpose as X. So it resembles this as X and this as Y. So that's the reason why we are doing it. We are naming it as X. Okay, let's go ahead. So when H gate is applied to register 1, X qubits, I mean, H gate is also applied to the X to the power n qubits. So we can't just expand and write all the qubits, right? Since we are generalizing, so why we are generalizing the equation, and we write as to the, let me write it clearly, H tensor product n, get 0 tensor product n equal to 1 divided by 2n. This is a summation. X belongs to 0, comma 1, get X, where X equal to X1, X2, X3 till Xn. Okay, so now again, we are writing the same thing again, 1 divided by root 2n, and you do the summation. And where do you get this, where do you get the 0? Get 0 to the power, I mean, tensor product n. This is the one. So we are applying this Adamat gate to first register only, right? So what will happen to the second register? It will be like that. So why? This is the second register. This is the first register. This is the second register, right? I will write this is the first register. So the Adamat gate was applied to the first register only. That's the second register. Okay. And this is actually step 2. So I think step 2 is done. So step 2 is also done. Now we'll be up. So since we put this input state in the superposition, we'll be giving all the superposition input state into the oracle. That will be our step 3. Step 3 is okay. Step 3 is query the oracle. Just a second. So we know that U f is x comma y giving x comma y f or, I mean, x or f of x. So the first register is X. So after the H gate, and the second register is initialized to get 0. This is the one. So in the formula we write get Y for generality, but in Simon we substitute get Y equal to 0, 1. I will explain you this. Okay. So from the previous one we got, let us write the previous one, 1 divided by root 2 to the power n. summation x belongs to 0, comma 1 and get x, get 0 plus 1. Okay. And now we are actually plugging this because we are using the we are inputting the this part into the oracle, right? So if you understand here, we are inputting, this is the oracle, right? So we have to input that. XOR f of x, okay, which is equal to x f of x. So what happens here? So what happens actually? So we are actually not writing this get 0 to the power to the tensor n. Why we are not writing? Why? What happens to this one? It's actually overwritten. In yesterday's session, we have gone through the XOR properties, right? Like I will also again just write the table of XOR gate. So A B A XOR B. This is an XOR gate. Okay, so nothing to worry. I'm just giving you this because to explain it much more better. We have 0 0 0 1 1 0 1 1. So A XOR B becomes 0 1 1 0. Okay. So what is the rule 1 here? Rule 1 is when A XOR 0, you get the same value A. For example, you take 0. For example, you take A equal to 0. So when A equal to 0, 0 XOR 0 becomes 0. Okay. So if you take if you take A is equal to 1, so 1 XOR 0 becomes 1. So you get the same value of A. So this is A. 1. So in this case, 1 is A equal to 1, so we get the same result. In this case, 0 is the A value, A equal to 0, so we get the same value 0. So same thing happens here. Since get 0 summation f of x is something similar to the above case, right? It's very similar to this case. If you observe, this is also XOR. So what happens is you get the, we can rewrite it as f of x XOR get 0 tensor n. So you can see that this f of x XOR get 0 n, which is similar to a XOR 0, right? So how, for in this above case, you get the resultant as A. So in the same case, you will get the resultant for this as f of x. So why we are writing it as f of x and get 0 is gone. I hope this is clear from this. In this way, we get the step 3 result. 1 divided by root 2n summation x get x into f of x. So this happens after we applied the input into the superposition input state into the oracle. Okay, so this, in this diagram we have completed this part. Okay, now we are actually measuring, going to the step 4, and we are measuring. In this diagram we can see that there is a measurement here, so we are actually going to measure this one. Okay, this part, this one. So step 4 is actually measurement. measure the second register. So the state before measuring the second register is 1 divided by root 2n summation x belongs to 0 comma n1 get x f of x, right? Now what happens when you measure the state? So actually we are measuring the second register state only. State after measuring the second register. So when you measure the second register, classical bit string is the outcome, because the only values lining in the second register are f of x. Okay, so your outcome. So you can see this in the second register, the only value is f of x, right? So your outcome must be one of them. So there exists at least one input x with f of x equal to y out. So pick one such input and give it a name, and so we write that as x naught. So actually, what Simon promises is, by Simon's algorithm, we are coming to the important point of the Simon's algorithm. I have explained this in the slide also, that Simon's algorithm promise is exactly mapping two input into the same output, right? I have mentioned that not to worry about this two input mapping to one output, because it is in the measurement stage. In the measurement stage, nothing matters. Measurement itself means it becomes irreversible. Means you can't. You are getting the solution. Okay, only the only between the operations, only from starting, before measurement, everything should be unitary. But when it comes to the point where measurement is being done, you don't have to worry, because measurement itself is makes the state to collapse. Okay, so by Simon's promise, two input map to the same output. So x0, x naught and x naught plus s. Okay, so you must get a doubt how come two inputs map to the same output. So just now I explained, this is just a measurement stage. When you measure the second register, you get a classical bit string. Okay, so that classical bit string is f of x naught. Measurement is not actually a gate, it's just a different physical process, and that physical process is actually non-unitary and probabilistic, and it collapses the entire superposition state to get the particular result. Okay, so it's inherently irreversible, and that's completely okay. So quantum computing only requires the unitary evolution between the measurements to be reversible. Only till measurement, till a stage before measurement, everything should be unitary. All the operations should be unitary. When it comes to measurement, it doesn't have to be unitary, because measurement is actually not a gate. It's just a process. Okay. So thus, after measurement of the second register, um, you get a classical bit string. After the measurement of second register, you get uh, classical bit string f of x0. Okay, because f of x0 equal to f of x plus s. That's the first register. So in this case, since the measurement is happening, the first register also collapses, and thus you get an equation like this. Okay. Or you can also write like this also, from in the oracle form. X f of x equal to y out is equal to x0 comma same thing. I just wrote the same thing, but it is in the oracle kind of format. Okay, so if you want, you can have this. Otherwise, you can follow this itself. So in this process, we have completed measuring this. Okay, so this part is done. Now we are going to apply the Adamant gate again. This step is going to be a bit more longer because there is a lot of explanation in this. Okay, again apply Adamant gate to register 1. Okay, so we all know that H gate, when it is applied, you get a resultant as, I mean, the matrix form as that. It's not a matrix form, but I'm just writing. When H gate is applied to gate 1 state, you get 1 divided by root 2 H0 minus gate 1. Okay. Now we are going to actually rewrite this H1. Okay. Equal to 1 divided by root 2 gate 0. We have gate 0 minus gate 1, right? We can take this plus here and then we can do minus 1 to the power 1. So if you do minus 1 to the power 1, of course it will be minus 1. So actually, in another point in mathematics, there are different ways to actually write an equation. We are actually trimming according to our needs. Okay, so why this equation is like this? The reason is we are actually trimming according to our needs. You can actually write mathematical equation according to our flexibility, what we want to solve. Okay, this is also one point when you are trying to solve a mathematical derivation in anything. When you're pursuing a theoretical mathematics, or you're just normally deriving a quantum algorithm derivation, you just remember this point. So coming back to the point, so for a bit b belongs to 0, 1. So if you give bit b, so the b belongs only to 0 and 1. So b can be either 0 or 1. Okay. So I'm just generalizing that this as b. Okay. H gate. When H gate is applied to b, you get 1 divided by root 2 H0 plus minus 1. I'm again generalizing it to b into gate 1. Okay. So you can remember, if b is equal to 0, if you put b, if you put minus 1, I mean, I will write it here, minus 1. If you put 0, anything to the power 0 is always 1, right? So you get plus. If b equal to 1, minus 1 to the power 1 becomes minus. This is a simple math. Everyone will know about it, but I'm just explaining you. Okay, since H gate is applied to the first register, which has n qubits, since we termed in step 1 as x, let's have it as x itself. So H gate is applied to hx. I mean, when you're applying H gate to the register 1, I've mentioned that register 1 has multiple qubits. So we have named that so many number of qubits as x. So let us keep that. Okay, when you apply H gate to that x number of qubits, we can just write as x1, x2, x3. These are the number of qubits in the first register. Okay. So when you apply H to the x1, tensor H gate applied to x2, tensor product till you tensor H to xn. See, just by writing a simple x1, x2, we can't. We are just going to the next lines. If you have multiple number of qubits, you can't write right. You can't just expand. You can't just keep expanding. You might lose a phase. So why we are again generalizing? So why this is the reason why we are generalizing a mathematical equation. So that if you're solving a simple problem, you can take that generalized equation and you can solve from that equation. This is the reason why mathematicians actually generalize the equations. So here H gate can be either in 0 state or 1 state. Okay, we can't keep writing. I mean, we can't keep expanding whether how many number. We can't keep expanding because it takes a lot of time and energy. Then what is the use of doing the quantum one? We can do the same thing in classical one, right? So for this reason, we are keeping a bit xi belongs to 0 and 1. So we can name this as I, and that I belongs to 0 and 1. Okay. So H xi equal to ket 0 plus minus 1 xi to the 1 divided by root 2. So you get the tensor product I equal to 1 to the power, I mean, n. The upper boundary is n and lower is I equal to 1. Ket 0 plus minus 1 xi ket 1 divided by root 2. Okay, so you're taking this outside 1 divided by 2, and then you're using I equal to 1 to the power to n ket 0 plus minus 1 xi ket 1. Okay, so when you expand, I mean, sorry, this is not summation, they should do this I equal to 1 to the n. So when you actually expand this one, for each position I, you pick either ket 0 or ket 1. So you actually collect those picks into n bit string as y equal to y1, y2, yn, and you can choose between. You can choose y equal to 1 if you picked if you pick ket 1 at position I. I know this can sound a bit more confusing. It should confuse because that's how it is made. I can directly even write an mathematical equation and go, but I don't want to do it because there is no use of just writing it. I am trying to explain as much easy as possible, though it doesn't sound easy. Okay, let's come back to the point. The tensor of all the picks is actually the basis vector y. When you tensor all the picks, those picks are actually the basis vector y. Thus, the expansion is a sum over all 2 to the power n basis state. Thus, the expansion is a sum over all 2 to the power n basis state. So we are writing this as 1 divided by root 2 to the power n. Summation y belongs to 0, 1 n. I'm just writing here a sign for y. I will explain why. Why I wrote y sign for y. So why it is sign y? Because every time you pick ket 1 at position I, you also picked up the factor minus 1 to the power xi. If you picked ket 0 at position I, there is no sign appears. Okay, so the total sign for y is the product I equal to 1 to n minus 1 x to the power I yi equal to minus 1 summation I xi yi. Now we have another important topic. When you do binary dot product, x dot y is equal to x1. You are expanding that as x1 y1 in x1 into y1 plus x2 y2. I mean, this is an XOR. Okay, xn yn. Thus, minus 1 summation xi yi becomes minus 1 x into y. And that gives you 1 divided by root 2 to the power n. Summation y belongs to 0, comma 1 to n minus 1 x dot y into y. Okay, so we are actually applying we'll be applying this to each term. Okay, so when you apply this to each term, here 1 divided by root 2 x0 plus you're applying command gate to, you understand, right? Where do you get this from? You got this from the previous results. You got this is the result we are actually trying to expand by applying this equation. Okay, again, sorry, you should have n here. Then you're taking, so when you apply Hadamard gate, you get root 2 n 1 divided by, 1 second, should not have. There is no n. I confused. There is no n here. Okay, we will get n in coming equations. Yeah, when you expand this n, I mean at Hadamard gate, you get it as 2 to the power n. Okay, not to get confused. Okay, so you get it as summation y minus 1 into x0 of y into kit y plus 1 divided by root 2 n summation y minus 1. Wait, let me now remove this and I will write properly because I can't write it. Okay, 1 divided by 2 and just n summation y minus 1 x 0 y plus 1 divided by, we're actually applying the Hadamard gate to these states. Okay, and we are just expanding that, but we are applying the Hadamard gate also. On top of that, we're also using this equation in this equation, using this in this. Okay, 2 to the 2n summation y minus 1 x0 xor x into y. Okay, so when you take these outside, you get 1 divided by root 2 n plus 1. You understood, right? How do you got 1 2 plus n? I mean root 2 n plus root 2 n plus 1 you got by taking this one and this one. I mean this one and this one and multiplied with this, you get, because those are common factors, right? When you take, you get this minus 1 x naught into y plus minus 1 x, I mean x0 x of s into y into kid y. So x0 summation s into y. We are expanding this as, so we are actually multiplying this and this. Sorry, this is, we are actually multiplying y inside this x naught xor plus s. Okay, so we get it as s into y. Okay, for a comma b belongs to 0 and 1. So you, this is another important point. Minus 1 to the power a plus a xor b equals minus 1 to the power a into minus 1 to the power b. Right. So in the same way, we are writing minus 1 into y equal to minus 1 x naught into y x of s equal to minus 1 into x naught into y into minus 1 into s into y. Okay, and then you plug back, what you get? 1 divided by root 2 n plus 1. You're plugging back in this equation. We just took this point and we expanded over this one, and then we are putting this whole thing back in this equation. Okay, minus 1 x1 into y plus minus 1 x0 into y, and then minus 1 s into y into k y. Okay, which is equal to 1 divided by root 2 n plus 1 summation y minus 1 x0 into y 1 plus minus 1 x into y into ky. Thus, we are actually not completing the step 5. We are still in the step 5 only. So you get something like this: minus 1 x naught into y 1 plus minus s into y ky. Okay. Now you have to read the amplitude. So for ky, this is the amplitude. Okay. For each basis state, for each basis state, ky, the amplitude is a of phi equal to 1 divided by root 2 n plus 1 minus 1 into x naught into y. So this is the this is the amplitude for ky. Okay, minus 1 s into y, and then here in this case we have two cases for this. If s dot y is equal to 1 mod 2, then 1 plus minus 1 s into y becomes 1 minus 1 is 0. So a of y equals to 0. Okay. Next, if s dot y equal to 0, 1 plus minus 1 s into y equal to 1 plus minus 1. So we are just substituting. Okay, nothing much. So anything to the power 0 is always 1. So 1 plus 1 equal to 2. So a of y equals to, sorry, 2. So there are two amplitude cases. We got one amplitude for, we got an amplitude for this y. Okay, and we are having two cases for this to solve. So first is a mod 1 mod 2, and then next is 0. And when it is 0, you have to, okay, so when you put back this in the equation, you get 2 plus 1 minus 1 x naught into y equal to minus 1 x0 into y divided by root 2 n minus 1. We are just putting this value in back in this equation. So nothing to actually worry about. Okay. Thus the state is 1 divided by root 2 to the power n minus 1 summation s dot y equal to 0 minus 1. This is the state. Okay, this is the state. So just now we completed the fifth state. So this is over. Okay, so we have completed this and we only have this measurement left. Measurement is very simple. Okay, it's just a small step. So we have done this much. We came this far. Next step 6 is measure the first register. Okay. In computational basis. In computational basis, you obtain a classical n bit string y with probability. So we are writing that probability as 2 to the power n minus 1 if s dot y equal to 0, if s dot y equal to 1. So this is the usual probability we get after measuring this. Okay, so every outcome must satisfy y dot s equal to 0 mod 2. Okay, so when you repeat this, when you repeat the circuit to collect several outcomes, so every outcome must satisfy this. Okay, so if you don't get the satisfying result, you need to keep repeating the circuit to collect several outcomes. You have to keep repeating the circuit. I mean, you have to keep measuring the circuit again and again to satisfy this condition. To collect several outcomes. Then you get an so each outcome like actually gives a linear equation, and you need to solve the system. When you solve the system with n samples, you get n minus 1 independent equation. So that within that equation, n minus 1 independent equation, the one which has a unique non-zero solution is the hidden bit string. Okay, so this is actually the mathematical derivation for the Simon's algorithm. I know this is a bit long. I don't think there is a mainstream place where you have this full coverage of this equation. I think we have actually done this. So this is the Simon's algorithm, and I'm also getting a bit late. So let me quickly share my screen to explain the hybrid quantum algorithms. My screen is shared, right? Yeah. There can be a lot of doubts in the Simon's algorithm. You please note it down and give it to Dr. Murthy sir. So he will send it to me. Then I will resolve the issues. Okay. So since I'm having some meeting in the next couple of minutes, I'm leaving. Okay, before that, let's see what are the important hybrid classical algorithms. So I'm just giving a very brief overview of what are the algorithms present. For example, you have something called variational quantum eigensolver. So the main core purpose of, let me put it in the slideshow view. Okay, so the main purpose of this VQ algorithm is to find the ground state energy computation, and also for the life sciences, you can do some drug discovery also. There is a benchmarking paper in VQA done. So for VQA is used in this drug discovery and then ground state energy computation. I myself have used VQA in one of my research paper. So yeah, so that's the main point in the VQA algorithm. And then yeah, the application areas are chemistry, material science, and drug discovery. And QAO is nothing but optimization algorithm. Okay, quantum approximation optimization algorithm. So the main core purpose of this is to solve the combinatorial problem, like traveling salesman problem, to find the best possible route to reach the location in a very short amount of time. So this is actually used in finance, logistics, and optimization. Okay, to find the best possible solution, people use QAOA algorithm. And next is quantum machine learning, where you use a classical machine learning path and into the quantum version, and then you have to train the model, and you can use it. There are some lot of algorithms like Kolmogorov and networks that were also there to find the K and Kolmogorov network is not a QML, but there are machine learning algorithms like SVM, neural networks. Those are used in the quantum motion as QNN, I mean quantum neural networks, and then quantum support vector machines. Those are actually used in quantum version of the machine learning, quantum machine learning. And yeah, the application areas are it is usually you can use it for the research purposes. So the main application area of the machine learning at present is to be used in the AI side only. If you're interested in QML, you can pursue that. But according to me, QML is in the research stage, and if anyone wants to make a career out of QML, then you need to do some research and all. You need to do some masters or some thesis. Don't do masters for QML. You can do a thesis in QML, and you can submit a paper if someone is doing bachelor's or masters. Okay. You can understand how QML algorithms work. And then there is something called hybrid quantum Monte Carlo algorithm, and the main application area is again chemistry and physics. And you have something called generative quantum eigensolver. So that's the generative quantum eigensolver is a new algorithm released in 2024 only, by one of the main person is from NVIDIA. So the main point in this GQA algorithm is you train a classical model. I mean the GPT model, what you're using. For example, you're using Chat GPT, right? So GPT, you have the LLM model, right? Similar to that, this algorithm is built upon that. Instead of chat, it creates a circuit, it generates a circuit. And till now there are only 2 research papers being published in the GQE, and there are a lot of maybe there are some other research group who are doing research in this GQE. I tried running this generative quantum eigensolver for some finance related issues, but I'm actually trying to do some finance related problem. So let's see how does it end. So the main application area for this GQE is chemistry, finance, and optimization. Hello. Okay.
Have
So
muted.
okay, sir. Okay. So the main, yeah, I just discussed about what is GQE. So till now, there are only 2 papers in GQE, and that too in optimization and the chemistry. They solved some, they simulated some hydrogen molecule, and they found some ground state energy, and it gives some very good, better results than the VQE algorithm. So yeah, if you want, you can pursue any other hybrid quantum algorithm that has a good research direction. Okay, you can also do a finance related problem also. Okay. uh, yeah, so this I have taken this from my book. This is actually taken from my book, Mastering Quantum Computing with Qiskit. And then we have yeah, all this problem formulation, everything I have written here. So I just shared the resources also with you. I think I have completed my session now. So if anyone has any doubts or anything, so please write it to Dr. J.S. Murthy, sir. He will give it to me. I hope he noted down the doubts and all.
Thank you, ma'am.
Thank
Thank
you,
you for
sir.
your nice session.
Thank you, sir. Thank you so much.
I know
Thank you.
the importance of your time. You
Yes,
can
sir.
log off.
Yes,
We will
sir.
continue, ma'am. Thank you,
So,
ma'am.
thank you, sir. Thank you so much. This was really very nice to interact with everyone. Yesterday's session was really good. And thank you so much, everyone. Yeah, thank you. Bye.
Bye, ma'am.
Bye.
Dear participants, I am sharing the session feedback link to you, and we will log in. We will rejoin at 7:30. Any issues?
Yes, sir.
Thank you. Thank you for understanding.